Hi everyone, welcome to the second part of Lecture 5 in Astronomy Geoscience 160. This lecture segment is going to focus on protoplanetary disks, which are the birthplaces of planets. So if we look at the planets in our own solar system, and astronomers have had a long time to do this, centuries in fact, we can start to look for patterns in them. And one of the most clear patterns in our solar system is the fact that all of the planets seem to orbit in a flat, orderly way. If you plot all of the orbits of the planets in our solar system and you look at the direction they go, all of the planets seem to be in roughly the same plane. There are no planets that are orbiting around the sun in this way. They're all orbiting around like this. They all orbit in the same direction as each other, and they all orbit in the same direction that the sun spins. So how do you get such a nice orderly pattern among our planets? And what can that tell us about how these planets must have formed? So one thing that we can infer is that in order to get all of the planets orbiting in the same direction, and all of the planets orbiting in the same direction as the star, and all of them to be flat, these planets must have formed from material that was in such an orientation to begin with. And material that all orbits in the same direction and is flat is what we call a disk. And this is how we think planets form. Planets form in protoplanetary disks. So here's what that process looks like. So remember, we've shown this animation a few times of how you go from a uniform ball of gas to something with small perturbations that grow and grow in magnitude and become denser and denser with more and more stuff together. And they start pulling everything close together. And then they start forming little filaments, which then collapse down into protostars. And these stars get hotter and hotter as they get more and more compressed, and they start fusing hydrogen into helium. So as this process is happening, let's zoom in on some of these newly formed stars and see what's happening in this simulation. So this video here is showing a simulation of many different stars that are forming. Right now there's only one, and now a few more stars are now starting to form, and then we have individual boxes showing them. So what I want you to do is to look at the diversity of what's going on in these simulations. And one of the things that you can see is that there's material orbiting around these stars. There's gas orbiting around these stars purely as a result of the formation. The gas collapses down, but not all of it collapses down into the star itself. There's still gas left orbiting. And it forms into these disks. The reason they form into disks is because that's kind of the lowest energy state. That's the state in which it's easiest for the gas to just keep going in the same direction. If you have gas that's orbiting in different directions, so maybe some gas is going around like this and some gas that's going around like this, it will collide with itself and it will no longer be able to continue in that same direction. So the only orderly way for this to happen is for the gas to rotate around all in the same direction in these disks. And you can see that this is a robust outcome of star formation. If we zoom to later in this video, you can see that almost all of these objects seem to have a disk of some sort or another. And you can see that the gas that's orbiting around them is all orbiting in these similar patterns. So this is what our intuition has told us about the formation from our solar system. And this is what our computer models have showed us. But is this picture right? So let's look at some observations to see if that's true of some newly formed stars. So in particular, let's look at this region in the sky called the Taurus molecular cloud. You can see here all of this beautiful filamenty gas that's emitting. The observations here are taken in far infrared light. So we're looking essentially at very cold things that are emitting black body radiation. And you can see that there are these filaments that look very similar to the ones in the simulation. We can zoom in on a particular area of this molecular cloud, and we can see several very interesting systems. You can see the gas that's still here, and you can see a star here and a star here. But first, let's look down here at this system. So this system has several interesting features. First of all, there is a flat thing that looks kind of like a disk here. It has two jets that are shooting out. So there's material that's both orbiting around this and shooting out the center. And then there's this area of gas over here. So this is a disk. We're viewing it edge on, so we're viewing the thin part. It looks a little bit hamburger shaped. And that's because we can't actually see through to the star because there's dust in this area as well. And the dust is blocking our view of the star. So if we could see through that dust, we would see the very bright star right here. But you can also see that some of the light of the star is escaping out the top where there's a little bit less dust to go through. That's why we see this glow here on top and this glow here on bottom. This area over here is called a Herbig-Haro object. This is what happens when energetic material that's being shot out from the jet, as it gets too close to the star, gets wrapped around by the magnetic fields of the star and shot out the top and the bottom, collides with another area of gas. It heats it up and causes it to glow like this. So one thing you might be wondering is, well, this is what it looks like in light we can see with our own eyes. What does it look like in other wavelengths? And the answer is if you zoom in on this disk, you can actually see in radio wavelengths that the disk is brightest at the very center here. So when you look in radio wavelengths where you can see where you can see cold things that don't emit light in the optical, where our eyes can see them, you can see it's actually relatively flat. And the only reason it looks like a hamburger to us is because we can't see through the dust in the center here. Okay, so let's look at another one of these stars. In particular, let's look at this one, HL Tauri. Now, this one is in a different orientation, so you can actually see that there's a bright star here and unlike this one down here, where you really can't tell that there's a star there at all. It's entirely hidden by the dust. So let's zoom in on HL Tau. This is what it looks like if you look at radio wavelengths. So again, in the radio, we don't really see the star. That's because the star is very hot and radio wavelengths let us see things that are relatively cold. But we do see this beautiful pattern here in gas and dust. And this is what the protoplanetary disk looks like. It's a little stretched, but that's only because we're looking at it a little bit oblong. If we were able to look at it from the top, it would be almost perfectly circular. And the key thing here to see is that there's structure. This disk is not a pure flat disk of gas. There are these rings and these gaps in the disk. Why would there be such things? This isn't the only disk that has similar structures. Here's one called Elias 227, a star called Elias 227, where this disk around it has these spiral arms. What is causing these spirals and these gaps and rings in the disks to exist? Indeed, these rings are fairly ubiquitous. If you take a look at a sample of many different disks and observe in these radio wavelengths, you can see that a lot of them have these very similar rings and gaps and spirals. So the idea is that the things that are causing these gaps and rings and spirals to exist are forming planets. The gravitational influence of the planet has mass and therefore tugs the stuff around it. And the way the planet travels through the disk as it orbits the star are enough to carve out these rings and cause these spiral features. These are simulations of what the gas in a disk and what any dust in the disk would look like when you have a planet orbiting where this white dot is. This looks quite a bit like what we've seen in our observations. So based on these, we're pretty sure that we can pinpoint where planets are forming within these disks based just on the patterns that they make. So here's a set of observations of disks. Here's a beautiful spiral. Here's the HL Tau disk I just showed you. Here's a few others that have these structures. And these are simulations of those systems when you put a planet in these particular locations. So if you put a planet in your calculations, in your simulations, at this location, planets at these locations, you can pretty much replicate what the observations are showing. So we think that what's happening here is that we're actually being able to watch planets being formed from the disks. And in the next lecture segment, I'll talk a little bit more about exactly how that process happens.